let's talk about cumulative distribution functions. One of the most common ways that I hear of the word cumulative is often during the last weeks of the semester, and students often ask, will the final exam be cumulative? Which means that, is it going to contain all the info that we've gathered up all the way to the end of the semester? The answer is commonly yes, but we can use that as our foundation to discuss cumulative or accumulated probabilities for a random variable. So the cumulative distribution function, that's a lot to write. Let's call it CDF. The CDF of a random variable such as capital Y evaluated at some specific value, lowercase y, is the probability that your variable will take on a value less than or equal to that specific value mentioned. So here I'm throwing out, that's a capital Y, here's a capital Y, and that's a definition of the variable that is being observed, right? Be it length, height, whatever, but lowercase, specific numerical values. Usually these cumulative distribution functions are represented with a capital F as like a function. And so for a specific value of your variable, the cumulative distribution function is defined as, capital F, a particular value from the variable is the probability that your variable is less than or equal to that specific value. It is often so much easier to consider new concepts in the context of an example, building off something we are already familiar with. So let's consider the coin flip example from the last video. And our random variable, capital Y, was the number of tails flipped in 3 flips of a fair coin. Right, we could have 0 tails, 1 tail, 2 or 3 tails, and we determined those probabilities in the previous video. And this was indeed a discrete random variable. This is a probability mass function describing the probabilities for this variable. Let's take a gander at the cumulative distribution function that would apply to this example. I'm actually going, because this is discrete, I'm going to create a function, but because it's discrete, we're going to have sort of different steps here. And I think I'll need a little more space. The probabilities are accumulating. And before there are 0 tails, if y is less than 0, there's no probability accumulated. If y, our number of tails, is equal to 0, and up to, but not including, 1, then we have accumulated probability 1/8. If number of tails equals 1, could be more than 1, but not up till 2, just shy of 2, we will have accumulated 3 more eighths. So here this would be 4/8 because of the 1/8 that came before it, and we are adding on the 3/8, so that would be 4/8 or a half if y, lowercase, is allowed to achieve a 2 and go up 2, but not including 3, we will now add another 3/8. So this would be the 1/2 plus another 3/8, which would be 7/8. And lastly, we can achieve 3 tails if y is greater than or equal to 3. We would add another 1/8 to what came previous. 1 7/8 plus 1/8 equals 8/8, which is a 1. All the probabilities added up must accumulate to a 1, right? So here we've got the cumulative distribution function written in a functional form here, but we can also display this in a graph. We love graphs. Let's see if I can fit this in over here. On the vertical axis would be the accumulated probabilities, so I will write capital F for our variable y. And over here would be our variable, capital Y, and the values that it can take on. It can take on values 0, 1, 2, and 3. And I'm offsetting the 0 here just for visibility's sake. Some tick marks that we might include for the vertical axis, maybe tick marks in a step of eighths. So 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8. Needed a little more space there. So 8/8, that's a 1. Here this is 4/8, which is a half, I know, but I think that will be nice. And so each tick mark is representing an eighth. Okay, let's draw this cumulative distribution function. The way this is going to look is like a step graph, where it kind of looks like a stepping ladder. So for y values less than 0, the probability accumulated is 0. So I'm going to thicken up my brush size here and display that as such. There would be a hole at 0 right here. So I will illustrate that with a hole. But once our variable is allowed to achieve a value of 0 heads, then the cumulative probability jumps up to 1/8. So that would be right here. That would be a solid dot. And it would be 1/8 all the way up till, but not including a 1. So I will draw a horizontal line and then illustrate a open hole there. Might need to make sure that looks more open. Okay. And once we can achieve a value of 1 tails, we would jump to cumulative probability of 1/2. That would be right around there. And again, going all the way over to 2, but not including 2, so open hole. Once our variable is allowed to achieve 2, our cumulative probability will jump to 7/8. That will be right up here. Again, flat line till our y value of 3, open hole, and once our variable is allowed to achieve a 3, then we can have our cumulative probability reach its maximum of 1. And that's what it will be forevermore. Generally, a cumulative distribution function for discrete variables will have this step function appearance because of the way that these must be determined. Because we're in discrete land, this function needs to be defined in a piecewise fashion. Because the function takes on different values, different probabilities for different pieces of our variable. Let's take a look now at cumulative distribution functions for a continuous variable and what this might look like. Well, there's going to be some similarities. For instance, both the discrete and continuous versions here will always max out at a 1 because all the probabilities cannot exceed 1. So it's maxed out there. And how might this look for a continuous random variable really depends on the type of variable and how it's distributed. One of the ones that we spend the most time on is a bell-shaped. So if this was our variable, let's see how its probabilities accumulate. Well, at first, they accumulate from left to right, kind of very small, right? Little bit by little bit are getting accumulated. That might translate over here as a very slight slope. But then it starts gaining speed and there's more and more probabilities and more, and so that's going to take a steep upward turn, and then they settle back down and go to fewer and fewer. So this would end up taking a turn again and asymptotically approaching the maximum value of a 1 there. Kind of fun. Another example of a random variable, maybe that is skewed, maybe right skewed. Let's see a different color here, green. If this was our variable, it's going to start off with increasingly larger and larger probabilities pretty dang quickly. So this would start gaining speed right out the gate. And then it will continue with pretty large contributions to the cumulative probability. But after we've reached that peak, they will start to lose steam in terms of the accumulating probabilities way over here. So this is going to kind of probably look more like that. These are pretty tough to draw in any accurate sense, but hopefully it gives you an overall sensibility of how probabilities are accumulating. So that's going to do it for this video. See you in the next one.